And here we go. So guys, last day of the unit. Wow, last day of the unit. Guys, we have 4 more days of lecture in this class. It's crazy. It's crazy. It's coming. So guys, here's what we're going to do today. We are going to talk about weak acid-base titrations similarly to the order that we handled strong acid-base titrations. When you learned about acid-base titrations, we started by looking at titration curves. That's where we're going to start today. Then we started to talk about how do you figure out the actual pHs along those curves. We're going to have that same conversation about weak titrations. And guys, what we're going to do is we're going to have this conversation sort of fluidly, if you will. We're just going to talk about it. But then, of course, the conversation is going to lead to some very practical things that we've got to do. And that's all summarized right here. So let's look at this really quick to make sure you see what you're looking at. So, and guys, maybe let me do this and bring this up then. So this is a strong titration curve. This is what we looked at last time, and you may remember that in this curve, and we'll talk more about this in a minute, we talked about this as having 4 regions: an initial region, a before equivalence region, an at equivalence region, and then a beyond equivalence region. And guys, you'll notice that that's the way this is set up. Initial, before, at, and after equivalence. And then guys, the top horizontal row is the strong titration stuff. So this is the tie back to what we did 2 class periods ago, where you figured out how to come up with pH. So guys, let's do this, and your neck's gonna get a little bit sore, but let's do this. Looking up and down and up and down and up and down, let's remind ourselves how we figured out the concentrations, or hold it up. Let's figure out how we figured out not concentrations but pHs at each of these positions, and then let's relate it back to this chart. So guys, looking here at region 1, which is the initial pH, and guys, remember the context of this, we are putting base into, it doesn't say it, but it was hydrochloric acid, and they're equal molarities. So guys, how do we figure out the pH of the acid before we put in any base? It's the negative log of the concentration of the acid, right? So guys, if this was it 1 molar? No, it's 0.1 molar. So guys, this is 0.1 molar, so in order to figure out the pH, it's just the negative log of 0.1. And guys, why does that work? What allows us to take the negative log of the acid's concentration, and that's the same as pH? Because it's a strong acid. It completely dissociates. And because it completely dissociates, 0.1 molar HCl is actually not 0.1 molar HCl. It's 0.1 molar H, and it's 0.1 molar Cl. But because it completely dissociates, the concentration of the acid is the concentration of the hydrogen ion, and that allows us to figure out the pH. Does that make sense? Ask questions, because guys, this is review. So questions if you need. You're good? Okay, so then guys, moving along, how do we figure out the pH before we reach equivalence? What does the math look like? Not icebox. This is strong titration. What do? We subtract, and so let's say we subtract, right? So what are we subtracting? What are the numbers that we're subtracting to come up with pH? The number of moles of the acid and the base that we've added. So guys, remember the way the math went. We had some number of milliliters of HCl. We went milliliters to liters, and then liters to moles, and we figured out how many moles of HCl we had. Then we took the volume of the base. We said whatever the volume of the base is, did a similar calculation. We figured out how many moles of acid, we figured out how many moles of base, and we subtracted them. Now guys, when we do that subtraction, what did that result in? Which one did we have more of, moles of acid or moles of base? moles of acid because we're before equivalence. So guys, we had more moles of acid than we had moles of base. And so the idea was, and let's write, so this is the reaction that's taking place, right? So the thought behind the math was that this calculation allowed us to figure out how many moles of HCl. This calculation allowed us to figure out how many moles of NaOH. We subtracted the two, and the difference between those tells us the amount of HCl that hasn't been neutralized. Does that make sense? So guys, then we took the number of moles of HCl that hadn't been neutralized, and what did we have to do with that before we could figure out pH? We had to divide by the new volume, and that allowed us to figure out the molarity that then allowed us to figure out pH. Is that coming back to you? Guys, if this is not coming back to you, go back and review the homework assignment we did 2 times ago. But guys, that's what this summary means. It says equal to the concentration of the unreacted ion, in this case the HCl, found by subtracting, and remember volume changes. Is that a meaningful summary of everything that's on the board? Is that okay? Guys, if there are pieces to that are missing, feel free to write them in these spaces. If you feel like I skipped something important that mentally you need to remember in order to be able to come back and do this, feel free to write it on this page. Okay? Then guys, this one's nice, right? The next, can I get rid of this? Not that it's horribly meaningful, it's really chicken scratch, but is that okay? So then guys, the next question was, what is the pH at equivalence? And that magic number is 7. Remember the idea is that when you've added equal moles, that's equivalence, when you've added equal moles of NaOH to the HCl, there's none of this, it's all been reacted up. There's none of this because it all reacted with the HCl, and the only thing you've got left is table salt and water, and sodium is a negligible acid, chloride is a negligible base, the pH is 7. Is that good? Okay, so then guys, if you understood this, you should also understand after equivalence. So remember, the math for after equivalence is exactly the same as the math before equivalence, but now the rules change. So guys, before equivalence, we had extra HCl. At equivalence, all the HCl is gone, so what are we going to have after equivalence? Extra NaOH. How do we then figure out the pH? It's still a moles-based subtraction, but guys, now we will have more moles, in this case of NaOH. So we figure out how many moles of NaOH, little dimensional analysis. We figure out how many moles of HCl, little dimensional analysis. We subtract. That will give us the amount of unreacted sodium hydroxide, divide that by the adjusted volume, take the negative log, and that gives us the POH, which we can then convert to pH. Yeah? Hold on, no, not yet. So, guys, is this an okay summary? Is that good? You're okay? Okay, and understand, I want to get there, but there's enough silence in the room. I'm afraid you guys don't understand this. So the idea is this: to figure out the pH after equivalence, you need to know how many moles of base. So let's say we're looking at that point right there. Okay, so you're going to go 70 milliliters of NaOH, 1,000 milliliters is 1 liter, 1 liter is 0.1 moles. Okay, then how many moles of HCl did we have? Well, it doesn't say this on the board, but it was 50 milliliters. We know that because the equivalence is at 50. So 50 milliliters, 1,000 milliliters is 1 liter, 1 liter is 0.1 moles, and we'll then figure out how many moles of NaOH, how many moles of HCl. Subtract. And that subtraction will tell us how many moles of NaOH are added in addition to equivalence. So figure out moles of NaOH, figure out moles of HCl, subtract the two. That will result in how many moles of NaOH are unreacted because all the HCl is gone and you're beyond equivalence. You will then take that, and molarity is equal to moles divided by liters, where moles is this. Liters would be 0.120 liters, the sum of the volumes, and there you go.
And then you would put that in the negative log.
But it would be,
You'd have to do 14 minus.
eventually, yeah, so it would be the negative log of hydrogen ion, which gives you POH, and then pH plus POH is 14, and go from there. Is that okay? Guys, great questions. Do you want to talk about this anymore? Oh, yeah. Guys, always write down, anytime you use an equation, write it down.
Even if it's the simple.
Oh, yeah, there's no such thing as simple. Anytime you use an equation, write it down first. They won't give you credit if you don't. Yep. You guys good? Are we buttoned up on this? Good review? Okay, so now guys, check this out. So this is a strong titration. Now, let's bring that back and look at what I did. I have now, well, I didn't. The book has now superimposed over that titration curve a weak strong titration. So guys, let's talk about the similarities and the differences between the two. So guys, first of all, let's talk about what we're titrating. Not surprisingly, it's acetic acid. I know. But guys, notice the similarities. So first of all, we're still titrating with sodium hydroxide. But also, I'll tell you this. You know what? Let's go green, because it matches green. So guys, this is 0.1 molar CH3COOH. I'm learning to not panic and just quit writing and just keep writing. So guys, this is 0.1 molar acetic acid. So the blue curve is the thing we just looked at, the thing we did to death looking at this. That's the 1 molar or 0.1 molar hydrochloric acid. The green curve is the 0.1 molar acetic acid. So guys, talk to me about the differences that you see. What do you notice? Give me one. Is so not just different, it's higher. We'll talk about that in a minute. What else do you notice? Yeah, so we've got an initial bump right here, and then it kind of tracks. It's a little steeper, but it kind of tracks. Okay, so we've got some concavity changes. What else do you notice? What do you, Rachel, talk to me about end up at the same place? What do you mean? Yeah, out here, they're indistinguishable. Yeah, good. We'll talk about that in a minute. What else do you notice? Yeah. Oh, good for you. I love that change interval. So guys, look at what's going on near equivalence. At equivalence in the weak titration, you'll notice, guys, that vertical section that's caused by that last necessary drop to reach equivalence is much shorter. And so you're right that this change would not be caught by methyl red, because methyl red would actually change color all the way back here and give you really wonky results. But what do you notice about where equivalence is reached? So, yeah, good. So two thoughts, right? It still is reached at 50 milliliters. So guys, we'll talk about that in a minute. But you're also noticing that the equivalence point is no longer at 7. It's now at 8.2. So guys, let's talk about this stuff qualitatively. Then we're going to talk about how to do this mathematically, generically, and we're going to relate it back to this and then we're actually going to solve some of these problems. So guys, let's clean up this mess and let's talk about the differences working from left to right. So guys, again, we need to remember that this is 0.1 molar, but now it's 0.1 molar weak acid. So guys, let's talk about this. Why is the pH of this acid higher than the strong acid? It's a weak acid. It doesn't completely dissociate, and so consequently the pH is initially higher. Now guys, let's talk about this concavity. This is not a big deal. We're going to talk about it for about 27 seconds, and then we're not going to worry about it anymore, but you observed it, so we can talk about it. Why does this pH initially spike? It initially has a very steep slope, very high rate of change, and then it starts to level off. Why does that happen? The answer is because the system is buffering itself. Initially, what happens is as you add this strong base to the acid, that strong base just tears this acid apart. But as it does, the product of that reaction is, and we talked about this 2 homework assignments ago. Guys, the product of that reaction is actually sodium acetate. And that sodium acetate actually contains the common ion that is necessary to buffer the initial acetic acid. And so what it's doing is it's actually self-buffering itself. And it's actually decreasing the rate of change in pH because of that self-buffering process. If that doesn't make sense, frankly, it doesn't matter, but that we're not even doing questions. That's what's going on. So now, guys, we get up to here, and then we find some interesting things going on. So let's talk about this first. Guys, first of all, the equivalence point is also at 50 milliliters, same as the HCl. Why would that be true? Yeah, and we should talk about this. We should mention this. Remember the HCl titration. The HCl titration was 50 milliliters of 0.1 molar HCl. This titration is 50 milliliters of 0.1 molar acetic acid. So guys, understand that the thought that we're about to share only holds true because the volumes are the same. But guys, here's what we're finding out. It takes the same number of milliliters of base to titrate the weak acid as it does the strong acid. Why would that be true? Go ahead. Yes. Does that make sense, guys? So I like the way you said that. Guys, it doesn't matter if it's a weak acid or a strong acid. They both contain the same number of hydrogen ions that need to be neutralized. Remember, titration is not an equilibrium process. This is a strong base. And it takes as much strong base to neutralize a weak acid a strong acid as it does a weak acid, because this neutralization process is a strong process. And this acid contains just as many hydrogen ions that need to be neutralized as this acid. The only difference is that in this solution, those hydrogen ions are all immediately available because this falls apart right away. Here, these hydrogen ions only become available as the weak acid breaks apart, but the sodium hydroxide forces this to break apart. So guys, the bottom line is this point of equivalence is at exactly the same place, whether it's a weak or strong acid, because it doesn't matter whether it's weak or strong, because the sodium hydroxide overwhelms it. Just a second, Rebecca, go ahead.
So if we have the same amount of hydrogen ion and hydroxide ion, and why is
Let's talk about that next. And there's a great, you're going to love the answer. You're going to hate the answer, but you're going to love the logic. Go ahead.
So it will drink
Let's look at the chemistry. So let me do this. I I want to do this in such a way that I can get back to this, and I think this will let me. So what do these titrations have in, what do these titrations have in common? And the answer, you know what, I'm going to write this a little lower. The answer is NaOH. The difference is the one in blue is HCl, and the one in green is acetic acid, okay? But when we do this, the products are table salt and water. So if we have 50 milliliters of 0.1 molar this, it's going to take some amount of that to neutralize it. When we do this, the products are still salt and water. It's sodium acetate salt, but it's still salt and water. We still have 50 milliliters of 0.1 molar this. So the idea is that this base doesn't care if it's neutralizing a strong acid. This is just a source of hydrogen. It could also be neutralizing a weak acid. It doesn't matter. It's just a source of hydrogen. And in either case, for every molecule of sodium hydroxide we add, a molecule of the acid gives up a hydrogen and it goes through to here. And it doesn't matter if it's strong or weak. The sodium hydroxide is still just attacking that acid one molecule at a time, pulling away a hydrogen and forming product. So it's a molar process and not a molarity process. It's a molar process. It all just depends how many molecules of this, how many molecules of that, and they fight it out.
And then it makes sense to say they're not equilibrium process, but it's a strong base.
Exactly. So yeah, and so remember we talked about this a little bit when we talked about titrating buffers. We talked about the idea that if we look at a buffer, we understand that the buffer is this, right? And so, and it's a buffer. And so when we add sodium hydroxide to this, the chemistry that takes place is for every one of these that we add, one of these dies and one of these is formed. That's what we're talking about here. For every one of these that we add, one of these dies and one of these forms. We're just looking at it in the bigger context of it being a salt, but that's the same chemistry. We were comfortable with it down here that this strong base just rips these things apart one molecule at a time. Same thing's going on here. This strong base is ripping these apart one molecule at a time. And it's the same, so the underlying thought is that anytime you have a strong participant, it forces the weak participant to behave as if it's strong, just one molecule at a time. Is that okay? Jake, did you have a follow? Or you wanted to talk about why not 7 point. Okay, so guys, are you okay with that idea? Okay, I'm glad that we did this because this is going to be a great segue into Jake's question. How am I going to do this? I'm going to go here, yes, there, back, there. Okay, so now guys, let's talk about this. I was zoomed in though, right? Yeah, okay, so let's talk about this now. I'm going to switch to black. I'll stay black because it'll make it stand out. So guys, why then is the equivalence pH not at pH 7? Well guys, in order to answer that, let's talk about why that's weird. Because remember, in our strong titration, the equivalence pH was pH 7. Does that make sense? So let's talk about why is the strong pH, or I'm sorry, why is the pH of the strong titration at 7 and the weak titration not 7? And guys, the way to think about that is this. Let's go back to what we just did. The answer is right here. So I'm going to make this stand out by choosing a really horrible color. So guys, this is our strong titration, and this is our weak titration. So let's do this strong first. Brandon, you need to hear this. So let's do it this way. So guys, in the strong titration, the equivalence is at 7. What about the weak titration? Where is it? Above 7. So let's talk about why. So guys, to understand this, and I know we've talked about this, but let's drive this home. What does equivalence mean? What's equal? The base and the acid. So guys, at equivalence, we have added an equal amount of this as there was that, so these are both gone. Where did they go? They turned into product. And what do we know about sodium ion? Worthless. What do we know about chloride ion? Worthless. What's the pH? 7. Now go down to this titration. At equivalence, what's equal? Equal amounts of this and this. So they're both gone. Where did they go? They turned into product. So our products are now still salt and water, but look at our salt. Our salt is now sodium acetate. What do you know about sodium? Worthless. What do you know about acetate? Not worthless. And so, guys, the chemistry that then takes place is this. This acetate ion attacks the water. And what does acetate ion do to water? Well, acetate's negative. When acetate ion attacks water, it forms this. That's a basic solution, and the pH at equivalence is above 7. Do you see it? Guys, that's what's going on is at equivalence in a weak strong titration. By definition, one of the ions in the salt is not going to be worthless. Consequently, it attacks the water and causes that equivalence pH to not be 7. In this case, the ion that isn't worthless is a negative ion, the acetate. It pulls the hydrogen off of water, leaving hydroxide and causing that equivalence pH to be above 7. Go ahead.
So what kind of like KB value do we
Well, and that's what we need to do, and that's one of the calculations we're going to do, because you're right. How do we then, and guys, this is where we're going, how do we then figure out the pH at equivalence? Icebox this.
Not iRace, just ice.
Just icebox. In order to figure out the pH at equivalence, what you do is icebox this. You icebox the ion that's attacking the water as a result of the neutralization. So that's the way you, and so then, Jake, as you're saying, you need the KB value. Yeah, does that make sense? You guys good? Okay, then guys, and this is what Rachel very insightfully noticed. Check this out then. What's going on after equivalence? They're exactly the same. But guys, think about after equivalence in the strong titration. Watch my hands. So at equivalence, equal amounts of acid and base, right? What do you got beyond equivalence? More base. You've added more base than you have acid, and so the extra base just causes the pH to go up. Well, guys, the same thing is true in a weak titration. You've still got acid and extra base, and that extra base causes the pH to go up. The acid neutralizes the amount of base up to the amount of acid you've got, and then any more base you add is just extra base that makes the pH go up. So it doesn't matter if it's a strong or a weak acid neutralizing that base. Thank you. It's still just extra base, and the curves are the same. Does that make sense? Yeah.
That exact salt and base won't be the same for every single base, acid-base solution.
They're amazingly similar. Yeah, they're amazing. Thank you. But you know what? We don't need to worry about all the what ifs. We just got to understand this right now. You guys okay? So guys, now let's relate this back to what you need to know. Grab the little table thingy that's in front of you and let's talk. So guys, let's do this first. Talking about the pH initially. It's not just the negative log of hydrogen ion because it's a weak acid. So what do we have to do to figure this out? Well, guys, this is our weak acid, CH3COOH, in equilibrium with CH3COO and hydrogen. That's what's in the beaker before we add any base. And how do we figure out the pH of a system like this? Icebox, not iRace. iRace is what we're going to do is we're adding base to this. But initially, none of this has been reacted. It's just icebox. So guys, you'll notice that was what this says, icebox. Okay? Now guys, what about in this region? Well, in this region, we are now neutralizing some of the acid with base. We are reacting up some of the acid with base. And guys, in order to handle that, that is this. That's this chemistry. We're taking the acid and we're reacting up some of it with base. That's an iRace box. Figure out how many moles of base or acid you have. Figure out how many moles of base you're adding to it. Represent that in our iRace structure and use that to figure out the pH. Okay? Now, guys, maybe the hardest calculation that you'll do in this class all year. How do you figure out the pH at equivalence? And so, guys, at equivalence, we already talked about this, right? At equivalence, what we're actually going to do, at equivalence, guys, what we're going to do is we are going to figure out, where'd it go? Oh, is it forward? There it is. So guys, at equivalence, what we've got to do is we've got to do the ice box that allows us to study the ion in the salt that's attacking the water. It's a simple icebox calculation. The thing that makes it ridiculously difficult is to figure out your initial concentrations. That's the nasty part. And then, guys, I don't even know if we need to talk about this. After equivalence, what does this look like? Well, guys, after equivalence, but this won't let me go back. Here we go. After equivalence, guys, it's just like before, it's just like the strong titrations. After equivalence, it's just a moles-based subtraction. So, guys, notice how I've represented that in this table. So, initially, ice box. Before equivalence, iRace box. At equivalence, you are going to ice box the ion that's attacking the water. And then after equivalence, you'll notice all I did was copy and pasted what's above it, because it's exactly the same math. It's just a moles-based subtraction. You get the idea? Okay. So guys, we're going to solve one of these. Here we go. Glad for the table, huh? Here we go. Guys, this is the problem we're going to solve. And we're just going acetic acid and sodium hydroxide. So it says this. It says calculate the pH of the solution that's formed when 45 milliliters of 0.1 molar sodium hydroxide is added to 50 milliliters of 0.1 molar sodium acetate. Textualize it for you first. You okay? So guys, let's put this in context and let's talk about what we're not talking about. Can I get rid of this? Okay. So guys, this is, what were our numbers? 45? Okay. So guys, here's what we're talking about. So the question that we're asking is this. We're looking at this green curve. We understand this green curve represents the titration of 0.1 molar acetic acid with 0.1 molar sodium hydroxide. So the question that we're asking then is, what is that pH right there going to be? The pH when we add 45 milliliters of base to the acid. Now guys, the thing that we are not going to look at, because I don't think we need to, but you need to know how to do this. What if the question asked, what is the pH before any base has been added? What would that look like? Just an icebox. Guys, you would go CH3 COOH equals CH3 COO plus. So guys, if they were asking you the pH initially, you'd simply go like this. You'd go ice, and you'd go 0.1 molar, 0, 0, minus x plus x plus x, 0.1 minus x, x, and x, and you'd throw that in a Ka expression and you'd solve. What's that?
0.1.
Yeah, you guys know how to do that. Okay. So guys, the question that we're looking at is this. What is this pH right here when we've added 45 milliliters of the base to the acid? So it looks like we're looking, the answer is going to be about 6. Let's figure it out. So to figure this out, we'll go back here, and I think that this provides us enough room to work. So let's just start on this. We need to create an I-race box. So guys, what are we I-racing? Guys, remember I-race boxes, whether it's a buffer or just a weak thing being titrated, is always formed on the weak electrolyte. So it's CH3, COOH. What? No, that's it. It's just written differently. And CH3, see, I wanted to spice it up for you. I wrote it different. I'm glad you're paying attention, though. And guys, what we're going to do then is we are going to, this is the space, right? Okay. So now, guys, we need starting values. This is a secondary calculation. You have room down beneath to do it. I don't. But guys, what do we need to know in order to get started? Well, the first thing, we need moles, because we're going to talk about how many molecules of acid did we start with and how many moles of base did we add. So to do that requires some moles calculations. So we've got 50 milliliters, 50.0 milliliters of our acid. You guys know this trick, right? You can call acetic acid HAC. 1,000 milliliters, 1 liter, 0.1 moles. So is it 050? All right. I'm so bad at pushing decimal places around. Yeah, okay. Oh no, I'm missing a 0. So guys, could you sign off on 0.0050 moles? Okay. Then, hey, while we're here, let's just get all of our background work done. That's all we need to fill in the top line of our I-race box. But we know that eventually we're going to need to know how many moles of acid we added. Or I'm sorry, base we added. So let's just do that right now. 45 milliliters. So 0.00450 moles. And that's HCl. Oh, HAC, sorry. HAC and NaOH. Would you buy those numbers? Okay. So guys, these are really all the numbers that we need to run this I-race box. So 0.005, and I'm going to be sloppy with significant digits because things are going to get cramped. So let's go back and let's plug this in. So our initial number of moles of acetic acid was 0.005 moles. This is none, and this is none. That's the primary difference between this and a buffer calculation. There is no initial concentration of acetate ion. Now, how much of this will be reacted? The answer to that is, how much base did you add? And the answer, as we already found out, is 0.0045 moles. So this is moles. So this would be minus 0.0045 moles. But then, guys, this is plus 0.0045 moles and plus 0.0045 moles. Yes? No. Yes? Is that right? Yeah, because each one of those is converted into those, right?
Well, we can end up with hydrogen ion if we're adding a hydroxide, or we can end up with water.
Oh, that's what's wrong. Thank you. Did you notice what I didn't do that got me screwed up? I didn't do this, and that's why I'm not thinking correctly, is this. The idea that this is the chemistry that's taking place, and that goes to water. I knew something was wrong. That's not true. This is still... This is still 0. I knew something didn't look right. That's still 0. Because that goes to water. That doesn't go to acid or to protons. Okay, so now our remaining amounts, and guys, was that okay, the change that I made? So the idea is we're starting with 0.005 moles of this, none of the others, we're adding base. The base will gobble up the acid. So how much base did we add? 0.0045 moles. So we will kill 0.0045 moles of acetic acid. That will be converted into 0.0045 moles of acetate ion. But again, guys, the other product of that is water. It is not hydrogen ion. And so we don't move the concentration of hydrogen ion. So the remainder of this is 0.0005. Is that right? Check my zeros. Am I okay? And then, guys, over here, it's obviously 0.0045. Again, these are moles. And then 0. So now what's our next step at that point in the iRace box? Convert, divide by the volume, which is 95, so is that 0.095? So 0.095 liters, 0.095 liters. So 0.0005, 0.095. So that makes this 0.00526 molar. And 0.0474 molar, and still 0. Can you guys sign off on that? My numbers look okay? Okay, so now, guys, what do we do from here? Now we're talking about the reestablishment of equilibrium. This is a rate-based equilibrium process. We understand that as this falls to equilibrium, this goes down by x, this goes up by x, this goes up by x. So we get 0.00526 minus x, 0.0474 plus x, and x. Am I okay? Yeah, but I need to go to another page. So I'm going to get rid of this. So then we've got Ka is equal to, and yes, you have to write this down. Nope, just that. Nope, yep, nope, yep, nope. So 1.8 times 10 to the negative fifth. Help me out here, guys. What's my numerator? 0.0474 plus x times x divided by 0.00526 minus x is approximately equal to 0.0, that's not a 0, 0.00526 0.0474x divided by 0.00526. So we have 1.8 times 10 to the negative fifth. Multiply that by 0.00526. Divide that by 0.0474. And my x is 2.00 times 10 to the negative sixth. And then guys, at that point, and you do need to do this, but I'm not going to, you go the pH is equal to the negative log of hydrogen ion, plug in the numbers. I'm not going to show that because we've done that a lot. And the number that I get is 5.70 for the pH. Do you buy that? What? Okay. Did we do okay? We good? So guys, then what we can do, just because I find it interesting, is if we go back here, we said that our number is going to be 5.70, and if we look at 45 milliliters, which is probably right in here, I mean, this is 5. This isn't, 5's not 5's. 5's here. So 5.70, given the crude form of this graph, I think we can trust it. Yeah.
So you said like the difference between various weak acid titration curves.
Uh-huh.
would be pretty minimal, right?
Yeah, they're pretty. But but here, the thing is the shape of the curve will always be like this. Where the particular lines lay down will be dependent on Ka, but you don't have to worry about it. It'll always be there. So, yeah, right. Exactly. So the shape will be the same, but they won't be superimposable because it changes by Ka. Okay.
And then weak-based strong acid would be the same thing.
Would go, yeah. So if we were, and guys, that's important, and you'll see this in homework. If we were doing weak-based strong acid, it would go like this, and then the equilibrium, the pH at equivalence would be below 7. Yeah. Okay. You're gonna go. Okay. Cooper, you're gonna want to really make sure you watch the tail end of this screencast. This is about to get crazy. You guys good? All right. So guys, here we go. Question 2. Calculate the pH at equivalence.
This is when things start getting crazy.
This is hard. Well, for those of you that struggle with organization, you're going to struggle with this. So guys, functionally what we're doing is we're figuring out the pH at equivalence. If it's helpful for you to have context in this, here's what we're figuring out. We're figuring out that number right there. It looks like about 8.2 or 8.3. So guys, let me take you through this adventure backwards. So how do we figure out what that pH is? Well, guys, and you don't need to write this down yet, but the question becomes, and maybe let me go clean screen so I can show you. The question becomes this. What chemistry, guys, think about it and don't write this down, just watch. What chemistry is going on at equivalence? And guys, the answer is this. The acetate ion is attacking the water, and that acetate ion is creating unprotonated acetic acid and hydroxide. So that eventually is the chemistry that we need to study. The problem is this. We are not told anything about the amount of acetate ion that we've got. So where did that acetate ion come from? It came from this chemistry. we had the acetic acid being attacked by the sodium hydroxide. This is the titration that we're studying. Acetic acid is reacting with sodium hydroxide. When it does, that forms sodium acetate. I shouldn't have put that charge there. When it does, that forms sodium acetate and water. This acetate is that acetate. So guys, the idea here is that to figure out the pH at equivalence, this is the chemistry that we need to study. Eventually, what we're going to do is we're going to study that by iceboxing this thing. But the problem is we can't just leap into the icebox because we're not given any information about this. So in order to infer this concentration, we've got to go back to the chemistry that created the acetate in the first place. You get the idea? So guys, this is the important connecting thought. You ready? How much acetate will this reaction create? No, not specific to this example. Generically, how much acetate will this create? What's the answer? How much acetic acid did you start with? Let's say that again. And did you notice I sort of hiccuped when some of you said sodium hydroxide? It doesn't really matter which one we talk about, but let's go with Brandon's answer first. So guys, do you understand what we're saying? Let's go back and go through this thought again. So in order to figure out the pH at equivalence, we've got to study this chemistry. We're going to icebox it. But we don't know where to start because we don't know how much acetate ion we're starting with. So then we need to ask ourselves, where did the acetate ion come from? Answer, from the titration. So then the question becomes, how much acetate ion was created? And the answer is, how much acetic acid did you begin with? Because if you know how much acetic acid you began with, it all got converted into acetate ion, so you will have the same amount of acetate ion as you started with acetic acid. Does that make sense? So why did I hiccup when somebody said sodium hydroxide? It's the same. Why is it the same? Because we're at equivalence. So guys, it's safer to start with how much of the acetic acid did you begin with. But you could start with how much sodium hydroxide did you begin with, because frankly it doesn't matter because it's the same. Do you get it? Okay, so now guys, now that you understand at some level the logic behind the calculation, now let's structure this in a way that you can remember on the AP test. So guys, it says this. You know what? Hold on. I need more space. So I'm going to take this, copy it, paste it, go down here, delete. Well, you can't see that, so it won't matter. Okay, now that'll give me more space. Okay, so guys, second calculation then goes like this. What's the pH at equivalence? This is the way to handle this. Play along with me. Here's what you're going to do. You are going to write down the balanced equation. Oops, that's not right. Sorry, hold on. You're going to write down the balanced equation for the titration. Why is it important that you do that? Because it allows you to figure out the chemistry at equivalence. So you look at this and you have the thought, sodium ion, what does it do to water? I know we've already talked, but let's pretend like we haven't. What does sodium ion do to water? Nothing. What does acetate ion do to water? Attacks it. So then, based upon that thought, You then go, okay, now I know what's going on at equivalence, and you can write your next equation that says the chemistry that I'm going to study at equivalence is the ion that attacks water attacking the water. So guys, I would strongly encourage you to write down the overall reaction first. That will then lead you to the ion that you need to focus on at equivalence attacking the water. Is that okay? Because it has to be. If it weren't, we couldn't do this. Now guys, we're going to icebox this. So now we need to talk about how, I don't know why, but this just makes me so happy that I get to do this. Okay. So now guys, we need to figure out how to jump into this icebox. And our entry point into this icebox is going to be right here. We need to know the molarity of acetate ion. And now guys, that's going to require two thoughts. Thought number one is, how much acetate ion is there? What's the answer? As much as acetic acid that we started with. So guys, now we need to do a secondary calculation that goes like this. At equilibrium, we have 50 milliliters of acetic acid. So we go 50 milliliters of acetic acid. We've already done this calculation, haven't we? Well, sort of. Yeah, we have. So guys, that is the number of moles of acetic acid. Moles. But guys, this is, and let's make sure we're clear, this is the amount of acetic acid we started with. But relative to the ice box, what is that now? It's not the number of moles of acetic acid we started with. The acetic acid's gone. This acetic acid is all gone. Where did it go? Got converted into acetate. So what is that now the moles of that we care about? The acetate ion. So we have 0.005 moles of this. That's what we started with, but it all got converted into acetate ion. So now we have 0.005 moles of acetate ion that's attacking the water. But guys, the problem is this. We can't put that in the icebox. Why not? It's got to be a molarity. So molarity is moles divided by liters. Moles is 0.0050 moles. What's our volume at equivalence? 100 milliliters, 50 of each. So it's 0.1 liters, and does that make it 0.05? 0 molar? Does it move the decimal up? Okay. So 0.050 molar. Now we can take that and plug that in here. And now we're iceboxing. Right? So this goes down by X. This goes up by X. This goes up by X. So this is 0.050 minus X, and X. Was that okay? So the tricky bit's this number, right? But now we're here. And now, guys, we've got to KB this thing. So in order to write down here, is that okay? Is that all right? I'd like to have it on the same page as this. So we're going to go KB is equal to CH3COOH, OH, and CH3COO minus, no water. So then we've got, guys, so we need the KB of that. Whoa. We need the KB of what? Nope. We need the KB of our weak base, acetate ion. They're not going to give it to us. Why not? Because they gave us the Ka of acetic acid. So now we're going to have to do another side calculation that says Ka times Kb is equal to Kw. Ka is 1.8 times 10 to the negative fifth times Kb is equal to 1 times 10 to the negative 14th. And we can figure out Kb. What? No, the K is 10 to the negative fifth. If I know one thing, it's the Ka of acetic acid. You don't mess around with me on that because it's one of the few things I actually can remember. All right, so 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative fifth. I'm going to go 5.6 times 10 to the negative 10th. So that then is our Kb. So 5.6 times 10 to the negative 10th is equal to x squared all over 0.050 minus x, which is approximately equal to x squared divided by 0.050. And then, guys, our x, so 5.6 times 10 to the negative 10th times 0.05, and then take the square root of that, and I get 5.3 times 10 to the negative 1, 2, 3, 4, 5, 6. So what is that? That's our concentration of OH. So can I move? You okay? You okay? So now, guys, we're going to do this. POH is equal to the negative log of OH is equal to the negative log of 5.3 times 10 to the negative sixth and that gives me a POH of 5.3, and then pH plus POH. Yes, you have to write down all these nitpicky equations. pH plus 5.3 is equal to 14, or pH is equal to 8.7. So 8.7, and if this doesn't line up, I'm going home. 8.7? Yeah. Never trust their graphs. So there's 5. It's perfect. It's perfect. Nailed it. I know, it's unbelievable. The difference is these graphs are just generic. So guys, what about this then? Hey, what would the calculation look like if we were past equivalence? Convert to moles, subtract, divide by the new volume. That gives you hydroxide concentration. Go from there. You guys good?
So if they were to just give us this right now.
Right now.
I mean, so if this was like part B.
Yeah.
Question,
Yeah.
Part C was what would happen if we added another 20
Yeah, right.
and we just convert to moles.
Exactly. Subtract. Yep. And that's exactly where this is headed. That very well could be one of the questions on the test. What? Yeah. It would definitely be one of the long form questions. So guys, here's your homework. I'm going to stop